Okay, let me just get rid of that box. Okay, good afternoon. Welcome everyone. We took a little bit of a break over harvest time because we were all pretty busy. And so now you're all back here for Office Hours with Dave and Anita. I can't believe it. This is episode 13, titled New Methods of Assessing Grapevine Evapotranspiration Demands and What It Means to You. To tell us more about this, we have Dr. Kaan Kurtural and Dr. Daniele Zaccaria. So, and if you're like me, you need reminding, this is November 17th, Tuesday at 2 p.m. So if this is the right place for you, please stay and join us for the next hour. We're going to have both Kaan and Daniele present for the first 20 to 30 minutes, all depending on how much we can speed them along. We'll have at least 30 minutes of question time. Just a slight reminder, keep yourself muted unless you want to ask a question. The best way to actually ask a question is to either virtually raise your hand or type a question in the chat box. When they have finished their presentations, we will check the chat box. We will read it out to the presenters and make sure that they answer your questions. But you can also raise your hand virtually and we will screen for you and give you a chance to ask your question in person if you would rather do it that way. So I was just going to say, you know, I'm supposed to introduce Kaan, and I was just going to say, you know, Kaan, my partner in crime at Oakville Experimental Station, but Karen was really nice and gave me a nice printout of all Kaan's credentials. So I'm going to be very professional. Things about Kaan you may not have known.
I have credentials.
Dr. Kaan Kurtural did his master's and PhD at the Southern Illinois University Carbondale in plant and soil science and plant biology. He started his career as extension specialist at the University of Kentucky. I'm sure somebody did not know this. And then moved to CSU Fresno as a professor, assistant up to associate, and then we stole him. And he came to UC Davis, Department of Viticulture and Dr as an associate extension specialist in viticulture, and he is stationed at Oakville Experimental Station. And Kaan, like a good extension specialist, works on basically everything that's grape and vine related. I almost talked about myself, including improving production efficiency in the vineyard, doing this by the canopy or irrigation management or mechanization, identifying quality traits for berry quality and how you can also improve this, and evaluating alternative methods for controlling invasive species in vineyards. That is just a very short summary of a long list of things that I know Kaan does, but we only have 30 minutes. So now, drum roll, it's over to Kaan Kurtural. You're muted.
Every time. I've been doing this for a year now. So anyways, today is my 5th year anniversary at University of California, by the way. Yay. So anywho, when Daniele and I talked about doing this a couple of weeks ago, we said like, well, let's try to do the best we can. So I'll introduce Daniele Zaccaria. He's my other partner in crime other than Anita. So Daniele came to UC Davis in 2013. He's in land, air, and water resources. He was the agricultural water management specialist. So he and I have various trials up and down the state of California, all the way from Hanford to Lake County, looking at these transpiration, evapotranspiration applied work. So without further ado, I'll turn it over to him for ET. He'll cover the large landscape sensing part, and then I'll give a brief overview of what we can do locally at the soil and vineyard level. So Daniele, take it away.
Thank you very much, everybody, for inviting me in this webinar. I discussed this with Kaan, and we decided that I will give an overview on methods to measure or estimate crop evapotranspiration with some specific reference to grapes. And so I'm going to share my screen now. And so you see, all right. This is the interesting part of technology that is useful when it works. All right. Can you guys see my presentation?
Yes.
All right. Okay. So the title of the presentation is New Methods to Assess Grapevine Evapotranspiration, but I think there's just a few methods that are new. I'm going to give an overview on the general methods that are used in California with various scale and level of accuracy for different purposes of water management. So I'll review some basics of crop evapotranspiration, and I'll describe methods to determine crop ET at various scales. And I'll talk about how do we use normally this information about crop evapotranspiration for what purposes. And if I have time, I'll talk about one specific research effort that we are about to start to improve agricultural water management in California, or with the aim to improve agricultural water management in California. So crop water use, I mean, the use of water by any crop, by any plant is an energy dependent process. So in other words, evapotranspiration, it's basically the transfer of water from the liquid state inside the plant tissues to the atmosphere. It is normally referred to as a water loss, but it is not actually a loss, because through water, the plant gets nutrients, and also it's a mechanism through which the plant can fix carbon and can elaborate the carbon in for building the carbohydrates. And this happens in the plant tissues, but also water transfer is very important to the plants to regulate the canopy temperature. So evapotranspiration is mainly driven by the amount of energy that is intercepted by the plant's canopy, by the vegetation. And there are different sources of energy. So we have the direct solar radiation, but also the plant intercept some scattered radiation, because the sun somehow is the main source of this energy, but then the atmosphere and the various particles in the atmosphere somehow scattered and reflect some of this radiation. So some part of this radiation bounce back to the plant tissues. And so we got direct solar radiation, and we got scattered solar radiation, and we got reflected radiation. But also there are other energy sources that somehow are intercepted by the canopy, and those are mass of warm air moving through the canopy, and we got also wind, and so some other type of energy that replace the air around the canopy. And in some cases, when our vineyard is isolated in the middle of nowhere or in the middle of nothing, so it is not surrounded by other crops, or is in the middle of the desert, we got also some advection, so movement of warm air through our crop. And so this is another source of energy. So it's not only the solar radiation, but there are also other sources of energy. So the combination of all this direct and indirect energy types and energy sources to the plant canopy are the process through which evaporation and transpiration are regulated. And evaporation and transpiration can happen when the soil moisture is there and is not limited. Otherwise, what happens is that the plant get this energy and increases its temperature, because it cannot dissipate the heat. All right, so there are different methods to determine crop evapotranspiration, and normally we, in the physics domain, we divide them into two main categories. So The first category is direct methods, and then there we have indirect methods. So for direct methods, we have in principle, we have the eddy covariance, and the eddy covariance is probably one of the most accurate methods. It's considered somehow the gold standard in measurement of evapotranspiration. And here I put the main equation, the main surface energy balance equation. And so in the eddy covariance method, we use normally towers. There are assembly of basically sensors. And this assembly normally include a sonic anemometer that measure the wind, speed, and direction in the 3 dimensions. And also we measure the concentration of water vapor and carbon dioxide through a gas analyzer, an infrared gas analyzer. So normally we have an assembly that is called IRGA, which also is coupled with the sonic anemometer. And this allows very high frequency in measurement of the movement of air and also the concentration of water vapor and carbon dioxide. So the two sensor, then they provide a direct measurement of the fluxes. So the fluxes of water, vapor inside and outside the leaves and the plant tissue, and CO2, which is basically important for photosynthesis. And so basically through this direct method, we can determine the amount of water that is evapotranspired through the canopy, but also somehow get a sense of the photosynthesis. So this is considered probably the most accurate measurement. And then we have the good old lysimeters, and those are somehow devices. There are large scale device, and normally they are basically they're giant scale that weigh the soil and the water and the crop with a certain frequency. And so those scales measure ET by accounting for how much precipitation gets into the soil and the amount of water that gets out of the soil through evaporation and transpiration. And normally those large scale are put in the ground, and they have weighing cells below, and somehow the crop grows into this big container of soil. And so the scale measure the change in weight over time, and through this changing weight, we keep track of all the in and out from this system in order to determine by difference the amount of water that we lose through soil evaporation and transpiration. The other direct method is through plant-based measurement. We have some device that measure the sap flow through the xylem, and basically we infer the loss of water through the plant tissue through the flux, through the flow of sap through a certain determined cross-section of the xylem. Those are more devices for measuring transpiration for scientific purposes, but there are some commercial version of this to simplify the measurement and estimation of crop evapotranspiration for growers for irrigation scheduling purposes. And then we have some other device that we call, again, IRGAS, or infrared gas analyzer. This picture gives an example of a portable IRGA, where we have instantaneous measurement of the amount of gas exchange from the leaves to the atmosphere, and the reverse, so water vapor and CO2, and somehow we can get an instantaneous measurement of the canopy stomatal conductance, and also the CO2 fixation. And so we can get a sense of an average flow of water through the stomata. And then we have to infer the amount of water that is transpired for the whole canopy by multiplying the surface area by this instantaneous measurement. So it's a very accurate, but at the level of leaves or individual stomata. But then when you have to infer the canopy size, the canopy volume, then we lose accuracy because we go with some sort of assumption. As far as the indirect method are concerned, we got here basically a two-step crop coefficient approach. This is a model to estimate evapotranspiration of a crop through the use of crop coefficient, multiplying a crop coefficient by a reference evapotranspiration. And a reference evapotranspiration is the amount of water that is somehow used by a reference crop that is in California is a grass, a 12-centimeter tall grass in optimal agronomic condition. And so a crop coefficient relates our crop water use to the grass water use through this adjustment factor, which is crop coefficient. Of course, in order to apply this method, you have to have some good, reliable values of the crop coefficient. I'll tell you a little bit more about this crop coefficient later. We can have a soil water balance approach. So we measure everything that gets into the soil and out of the soil in order to determine the amount of water that is used by the crop by somehow difference. And this approach accounts for the balance between precipitation, irrigation, deep percolation, water flux upward, and surface runoff, and somehow the changing storage of water over time. Those are mostly calculation procedure, and so being somehow a modeling effort, they are affected by some assumptions, and if the assumptions are not accurate or not reliable, then our accuracy in the estimation of ET probably will suffer. And you know, another case is the use of remote sensing techniques, and we got different methods here through thermal, infrared, and multispectral. Basically, we can measure we can estimate different parameter of the surface energy balance through this combination of thermal imagery and multispectral imagery. We can have microwave, the use of microwave technology for monitoring the soil moisture over time, and this soil moisture observation can then somehow can be coupled with meteorological data for getting a sense of the amount of rainfall that is falling on an area, a crop area, and also temperature, wind, and other meteorological parameter. And then we got some other way of estimating the ET through remote sensing, what is called reflectance-based crop coefficient. So through the use of vegetation indices like NDVI or EVI or SAVI, we can somehow infer the amount of canopy cover, and from the amount of canopy cover, we can estimate the amount of energy that is intercepted by our crop, and infer a crop coefficient through some research correlation that has been developed from trials, from scientific trials. Once we get this linear or semi-linear relationship between the vegetation indices and the crop coefficient, then we can multiply this vegetation-based crop coefficient by reference ET and obtain a sense of the crop evapotranspiration. Now, in terms of energy for the process, as I mentioned to you, basically the evapotranspiration is an energy-dependent process, and the main source of energy again is the sun. And so this solar radiation, when it gets to the crop surface, part of this radiation is reflected back to the atmosphere, and part is filtered through the atmosphere and it gets onto the soil. If the soil is wet, this amount of energy generates soil evaporation. If the soil is dry, then this energy generates change in the soil temperature and what we call G, the ground heat flux. Okay, and so when this energy basically hit the canopy, if the canopy is well watered and so has access to water in the soil, then this energy is dissipated through the process of transpiration. And so there is some sort of partition of this energy into different components that I will talk to you a little bit more in detail in the next slide. So with this partition of energy, what we try to estimate is this parameter LE, which is the latent heat flux of vaporization. And this latent heat flux of vaporization is somehow equal to the sum of the energy that hits the surface minus the amount of energy that is stored into the soil minus the energy that is somehow used to heat the air above the canopy. So this is the simplified surface energy balance equation that we normally use in studies related to crop evapotranspiration. Now, this is a practical example of a vineyard in California, and I put here the surface energy balance equation again, just for recalling the concept. But what we normally, what we normally do when we measure evapotranspiration in the field, we try to either measure this LE, which is the amount of energy that is being used to evaporate or transpire water. And we also measure a net radiation, which is the amount of energy that is available to do the work of the process of water vaporization. And so we measure this component that is called net radiation. We also measure the amount of energy that is conducted into or out of the ground. And we measure the amount of energy that is used to heat the air around the canopy. I'll give you a little bit more detailed example of instrument that we normally use in the field to determine the actual vineyard evapotranspiration or the evapotranspiration for any other crop. We normally use the residual of an energy balance method. And again, these are the equations. So the component of net radiation, ground heat flux, and sensible heat flux, or Rn, G, and H, are normally measured with the specific instrument. So in case of net radiation, we use a net radiometer, which is here on the left. And then for the ground heat flux, we measure through two types of sensor. There are temperature probe and heat flux plates that we place in the ground at a certain depth. And then we measure the sensible heat flux through two types of instrument. One is called sonic anemometer on the top picture, and is a three-dimensional sonic anemometer. And we use this instrument, which is pretty expensive for scientific purposes, and we apply the eddy covariance method. Or in parallel, either or, we measure also the sensible heat flux through change in temperature, very high frequent measurement of change in temperature over time through a different technology that was developed at UC Davis that is called a surface renewal. And this is a much cheaper instrument and a much cheaper sensor, and is basically a fine wire thermocouple. Now, these are examples of application of this technology of the residual of energy balance in vineyards in California. As you can see here, the different pictures with different setup for scientific research purposes. And of course, when we measure ET, we also try to collect some additional measurement that are specific to say that we are measuring a well-water vineyard or well-water plant. And so in order to establish if the plant is well watered, we normally conduct measurement of leaf water potential or stem water potential. As you can see in this bottom pictures here, we have a, a portable pressure bomb that we use for some of this measurement. Now, the residual of energy balance method can be applied with all ground instruments, all ground sensor. As you can see here, here is a full flux tower that has an installation in Pistachio, I think. And we got sonic anemometer here, net radiometer, and also ground heat flux. Or some of this parameter can be also estimated through remote sensing, through satellite or airborne platform, as you can see here. In some cases, we have different accuracy with ground instrument and with the remote sensing, and I'll tell you a little bit more about. So what I talked about, it's either full ground measurement or full remote sensing techniques, but also we're working on a hybrid method that somehow combine the use of ground measurement with remote sensing estimate. So some of the parameter of the energy balance are determined on the ground, and some of the parameter on the energy balance are determined from airborne or satellite platform. Again, here's the equation. For instance, in this case, the hybrid methodology will generate an estimate of the net radiation through either airborne or drones. And here you see an image with the spatially distributed net radiation, which is the main parameter for ET. But also we can, through the drone or airborne or satellite, we can get a sense of the canopy cover, the canopy temperature, the soil temperature, and also generate some vegetation indices. There are additional information to see how big is the canopy, how happy is the canopy in terms of water. Okay, and on the ground, we can measure the sensible heat flux either with research scale instrument like the tower or the assembly that I show in the previous slide, or with commercial sensor. In this case here we have the Thule sensor, which measure basically a sensible heat flux with fine wire thermocouple. And so by the combination of these two, ground measurement and remote sensing, we can combine and get a better accuracy estimate of the actual crop ET. That means the amount of water that is transpired by our crop in the site-specific condition of our field. Okay, here is another example of ground measurement versus ET from a hybrid approach. In the ground measurement, we basically measure all the parameter on the ground. Here you can see sensible heat flux measured with a sonic anemometer, and net radiation measured with a net radiometer. And in the hybrid method, we measure only one of the parameter on the ground, which is the sensible heat flux, because it's easier to do on the ground, it's probably more accurate, and we estimate the net radiation through a GOES satellite, which is a geostationary environmental satellite revolving over the ground every day at a certain time. And so the combination of net radiation from the satellite and sensible heat flux from Thule will probably give a better accuracy than either only remote sensing or only ground measurement. All right, and so when we do this at the research scale, normally one of our flux tower is probably summing up to $15,000. While when we do this on an operational scale, and this is available commercially for growers, the cost of this technology is probably, the hardware is about $250 to $300, but this is also provided as a service. And so you, as a grower, you get the data. You don't own the hardware, but you get a service. You get ET in inches every day to your tablet or mobile phone or computer. All right. So when it comes to methods for estimating ET through remote sensing, there's a plethora of methods, and normally those are models that are being developed in a different location for different crops. We got the first one, it's vegetation-based, vegetation index-based crop coefficient. It's called SIMS and was developed by NASA and California State University in Monterey. And this is one method developed in California. There's other surface energy balance model like CBOL, metric SEBS, and other more accurate or more sophisticated, more complicated model that couple sub-model like hydrologic models and atmospheric model. So in the remote sensing, there's a fast progress for estimating ET on large scale or on broad landscape, but the level of accuracy for irrigation scheduling is still a little bit questionable for many reasons. I want to show you the results of a study that we have conducted on pistachio grown on non-saline and increasingly saline soils in the Central Valley of California, in the San Joaquin Valley. And I want to show you what we got comparing the data from one of this remote sensing model versus the data from ground measurement from our flux towers. And here, for instance, on the graph on the left, you got on the y-axis the ET in millimeter per day estimated through this remote sensing model. And on the x-axis, you got the ET in millimeter per day measured with our station. And you can see here, this is the one-to-one line. It means if the points are aligned along the one-to-one line, so there's basically a good correlation between the ground measurement and the remote sensing. But the good correlation is not there because we have someday overestimate. I mean, there's large difference between the measured ET on the ground and estimated ET through remote sensing, and there's overestimation and underestimation. So the graph on the right, it shows all the day of an entire season. So, and this includes satellite overpass day and non-satellite overpass day. And you can see there's a pretty remarkable difference, especially in the purple points. These purple points are high saline or moderately saline orchard. And so when the salinity somehow kicks in some metabolic and some physiological reaction in the tree, then this is the time when remote sensing somehow, according to what I observed, start lacking accuracy. Now, here's the metric that we developed comparing the remote sensing versus the ground. And you probably should see the column on the mean relative difference. And you can see here that on an average base, we got 25% difference between ET estimated with satellite and ET measured on the ground, 25% with a very sophisticated remote sensing model. I don't think is really acceptable for irrigation management or for high value crops. Like pistachio for managing irrigation or scheduling irrigation. So we, in some cases for medium saline, we got 43% difference between ET estimated with remote sensing versus ET measured on the ground. So this remote sensing has always been promising, but I don't think we reached the point of very accurate estimate of ET in California because of the micro irrigation and because of the high value horticultural crops that have specific dynamics in terms of water use. I want to show you also the results of a study conducted by UC Davis and the Department of Water Resources on the Delta on many different crops. And so a team of scientists, basically there were 5 teams of scientists, run their remote sensing models for estimating ET on the delta. And you can see here on the graph below one specific day in July when the canopy is fully developed for all the crops, so like corn, potato, rice, tomato, and almonds. And you can see the level of differences in estimate that you get with the different models. And here is the summary of this. As you can see on the x-axis, we got the different, like 6 different remote sensing models. And on the y-axis, you got the amount of ET estimated, and you can see large differences between all these models. And so basically, models are full of assumption, and I think relying only on the model is not enough. For water management in California, we need a lot of ground truthing and not a lot of validation and a lot of work on the ground in order to make these models more accurate, at least to converge to similar value between all of them. One of the main problem is the pixel resolution with remote sensing. Here is basically, even when you have 1 meter resolution with an airborne, in a pixel you get the canopy of a grape, the shaded area, and the soil area. So basically you got reflectance from a blend of canopy, soil, and shade. And this is basically confounding a confounding effect in terms of the parameters that are needed for estimating ET. I'll stop here because I don't want to take too much time out of the presentation of Kaan, and I'll be happy to entertain any question. And the presentation will be made available if you need. Okay, thank you.
Great, thank you, Daniele, for that. For the great talk on ET and all the different kinds of ways of measuring it, including some of your more advanced research methods. I would say at this point, what I'd like to do, I do want to give Kaan a chance to talk, but you're still muted, Kaan. But
oh, okay.
So what I would like to do at this point is I'm going to kind of prompt Kaan a little bit on the kinds of things that I think we'd still like to cover. In the meantime, I'd like to encourage everybody to start asking questions in the chat, or you can raise your hand in the participants panel if you'd like to ask a question live. But I think, Kaan, one of the things that I think we'd like to do is, being able to take ET measurements, whatever way we can measure them, and understand how would we be using those measurements to make decisions on when to start irrigating and how much to irrigate?
Well, I hope I'm not still muted, right?
Nope, you're good.
Water in California is relatively cheap compared to other inputs that we have. We're used to this, cheap resource. However, as it's getting more scarce, the cost of delivering the water is what's affecting people. So using the crop coefficients, however they may be calculated, and I'll refer you back to Daniele on the big C3 project we have now. These are used to apply the fractions of deficits that we want to apply to grapevines. Last 30-35 years, we focused on heavily on the deficits, but as things have changed very drastically since the 1990s, we're seeing that a sustained deficit, whether it's like 70% in the San Joaquin Valley, about 50% in the Napa Valley or coastal ranges. We're seeing these, to be more beneficial rather than, applying like constant regulated deficits year after year. So that's how we have been, advising people to, apply the water at this point.
Great. There is actually a question in chat. Will Sentinel-2 solve any of the issues Dr. Zaccaria saw with the Landsat RM accuracy?
Yeah, well, some of the issues relates to the low spatial coverage, because basically in the Landsat satellite, you got an overpass every 16 days. With Sentinel, we got much more frequent overpass, and so this helps. But still, I think the optical resolution is too low for irrigation scheduling and for more accurate and precise irrigation management. So the improvements are coming along, but I don't think we're there yet in order to implement this technology for irrigation scheduling of high value crop in California yet.
So Kaan, quick question. You talked about the benefits of using deficit irrigation, but is there any detrimental effect to long-term deficit irrigation if we do this now for 10 years in a vineyard?
Yes, we just finished this work. What we don't see is the underground portions of the vine, the roots, the forgotten organs. A lot of the structural carbohydrates and non-structural carbohydrates are going to be stored in the roots. So when we ran this trial over the course of 5 years at Oakville, where we don't irrigate as much, we end up seeing the root mass and root starch decline by half each year. So what came with that was reduced fruitfulness in the upcoming years. Or the subsequent years. So we essentially devigorate these vines for no reason in hot climates with these deficits. Then with the wine work we did, we see these deficits that some people might be applying to be too detrimental, because we're seeing a lot of degradation of polyphenols in the wine compounds. So.
Okay.
This is another question from chat. I use ET to develop weekly irrigation schedules, which works okay. What are the best methods available to determine when to begin irrigation in the Central Valley and when to end irrigation post-harvest?
All right, I assume this is for grapes in the Central Valley, because every crop is somehow different. But I would say ET always have to be considered in combination with other parameter, and other parameters would be soil moisture, so the availability of soil moisture. So probing soil moisture monitoring unit is crucial to determine when to start irrigation, and every year is different. We see now a big swing every year in terms of rainfall, and so every year is different. So I would say probing or soil moisture monitoring units for monitoring the soil moisture are important, along with ET for deciding when to start irrigating any crop in the Central Valley. I would add that if the grower has the ability also, having some plant measurement will be also important over the course of the season. Probably not at the beginning, because the leaves are not well developed, and so those methods for plant-based water status require that the leaves are well developed. But I would say a combination of ET and soil moisture for when to start irrigating is probably the best thing to do. And when to stop irrigating, well, this really depends on the strategy that the grower wants to follow, and the type of target, and how the season has proceeded up to the harvest. So I would say there's not a general recipe for deciding when to stop irrigating in the Central Valley. It really depends on many different factors.
So a natural extension of that, I think to Kaan, but anybody's welcome. Will a late season deficit then be beneficial for berry and wine quality?
No, it will not. The largest demand, both from evapotranspiration point of view and from the plant demand, is right after veraison during engustment. And since sugar influx is what kickstarts anthocyanin biosynthesis, you need the correct amount of water post veraison, what we would call a late deficit. So at this point in time, we have not seen any benefit of restricting water or applied water to the plant. In regions where precipitation is limiting, well, this year, Napa Valley, it was limiting. We had about 250 millimeters of rain the whole water year of 2020. So this had to be supplemented. Likewise, even in years where we receive, close to 800 millimeters, late season deficits has not helped, and in fact was detrimental to first yield, and then of course compounds that we are after in red and white wine grapes.
What about, okay, so this is now a non-vineyard person question. So what about if you're trying to get your grapes riper faster, even if it's just plainly through dehydration? Won't deficit irrigation help then?
Well, I mean, after 21 bricks, vinifera vines do not make any more sugar. After that, it's controlled dehydration anyways. But, after that point, our peak ET is third week in July, which coincides with, veraison in most cases if you're a Cabernet grower. So if you want to ripen them faster, you just need to keep the photosynthetic machine, going. Because when we did the long-term irrigation trial at Oakville, 25, 50, or 100% of crop evapotranspiration replacement ripeness, or like a speed of ripening, was not necessarily affected on a 110R rootstock. But then, we do not see the, rootstocks, affect these processes much directly, other than, exploring, soil to a deep water most of the time.
So there's a question in the chat, and you just sort of touched upon it, that asks, how do different rootstocks affect the ET and irrigation water needs?
I'll tackle that one, since we worked in Kern County with a plethora of rootstocks in a former life. Rootstocks indirectly affect canopy architecture by sheer size, by active leaf area. Since grapevines are structural parasites, they have to reach for the sun, and to reach for the sun, they put on a leaf area. So when we compared Freedom 1103P, Salt Creek Ramsey, and Harmony against each other under various deficits, the largest grapevine always, wins out, because that can generate the proper leaf area, therefore the root mass. Evapotranspiration is driven by radiation, and then the water evaporate from the leaf area. So that's how they affect evapotranspiration. Yeah, desert climates is pretty good to do that kind of research.
I just wanted to break in and just let everybody know that we've scheduled our next office hours with Dave and Anita for December 15th. And Kaan will be coming back and joining us along with Andy Walker to talk about assessing fire damage in the vineyard, which is something I know is at the top of a lot of people's minds this year, unfortunately. So that will be on December 15th. It's again Tuesday at 2 o'clock, like we always do office hours with Dave and Anita.
Yeah, we'll do some bud dissections to look at some things. And
Caroline just put into the chat the link for registration for that.
So do we have time for more questions?
Yes, we do.
Okay, so Kaan, as
yes.
slow in the chat, I will fill in. So what about water recharge? Is this a recommended groundwater recharge? Is this a recommended practice for a vineyard?
Groundwater recharge is mostly done in the San Joaquin Valley and the river areas in District 13 and Lodi. When we work with groundwater recharge in southern San Joaquin Valley, it was driven by our previous work where, precipitation before bud break is what determines yield components in the subsequent seasons. So in years where these droughts have taken hold, groundwater recharge has been beneficial to bring up the water level in that soil profile, because in the end we're always in a deficit in vineyard situations, because Daniele can better explain the theory of deficit irrigation better than I can, because we always want to apply less than what the plant is drawing, without trying to use the soil potential of what has been stored in the soil. So you're actually using the grapevine as a wick at this point to tap into that deeper water, and the groundwater recharge certainly has helped with that. But that again depends if you have the water in this case. So last year in Oakville, by the time we came to finish the water year, by the time bud break happened, we only had about 23% of water volume by volume in a 5-foot profile of soil. So yeah, I mean, yields were lower in this year, but we cannot do a groundwater recharge here.
So we have 2 questions in the chat, and we have about 5 minutes left. So just so our speakers have an idea. So the first one in the chat is, can either Kaan or Daniele talk briefly about crop coefficients and how they relate to irrigation scheduling and the calculation of, and also talk about just the calculation of crop coefficients?
All right. So we normally use crop coefficient to schedule weekly irrigation for different crops, and there's an innovative product that has been released by the National Weather Service that is called FRET, Forecast TT. So basically, you can get every day forecast for the next 7 days in all the continental US. This is basically a forecast of reference CT. So if I have a reliable value of the crop coefficient on my specific crop, then I can schedule irrigation for the week to come. Now, the problem is that most of the work that is being conducted in California on crop coefficient has been conducted during the 70s and the 80s. And this is one of the reasons why we just got basically a large grant with the U.S. Bureau of Reclamation, and I'm sharing my screen again now. In February 2018, the Department of Water Resources and UC Davis and UCNR established this California Crop Coefficient Science Collaborative, and we held a launching event in April 2019, and then we got a first grant in 2020, in January 2020, that now is under contracting phase, and we are going to review the crop coefficient information for 10 major water demanding crop in California, including almonds, pistachio, grapes, alfalfa, most of the large water demanding crop. And we're gonna create a web repository of peer review crop coefficient information, because this is really a gap in our water resource management and planning. So this is just the beginning. This is a 3-year grant with a total funding of $720,000 that we just got in order to create work groups and review the information that we have available for table grapes, wine grapes, almonds, and develop more reliable crop coefficient information for irrigation scheduling and for water resources planning and management in California. So this is an important step for improving water management for the whole state of California. So I'll be happy to provide more information, in any time about this grant that we are about to start in February.
Great. Thank you.
So for those crop coefficients that they're asking about, we used to use the tried on our old method using the shade cast beneath the grapevine. However, depending on where we went, we were seeing underestimation or overestimation depending on row orientation or if you were on slopes. So we have now resorted to using the sensor data and dividing it by the actual ET to derive a more accurate crop coefficient. With that, we've been able to maintain what we wanted in terms of deficits and quality in wine grape vineyards at Oakville.
So there's another question, perhaps there's time. Should one irrigate isohydric cultivars differently compared to anisohydric cultivars? Did I pronounce that correctly?
Yes, you did. Yeah, I don't know why people are still hung up on these terms. There were two recent papers that were published by the late Professor Mark Matthews and one of his former students. Basically, under California conditions, there is no isohydric or anisohydric. The plants behave pretty much the same. If you move them into a greenhouse situation and call them well watered or deficit watered, then they might behave differently. But in nature, they pretty much behave the same. So I don't see any difference amongst these cultivars, and literature backs this up.
Dave, perhaps ask the last question for those.
One more question. We'll see if we can sneak it in here. Could we induce leaf senescence with water stress after harvest as a way to save water, and how necessary would it be to maintain some soil moisture over the dormancy period?
Our soils, unless you're in a Tehachapi desert in Kern County, they never go like completely arid. So we do want to maintain moisture, at least 25% volume by volume in the top 5 feet. The first foot will dry immediately, but I do not recommend inducing leaf senescence prematurely, because grapevines never truly go dormant in California like they would do in temperate regions. So we want to keep them on as long as we can, because the grapevine has an indeterminate growth habit, unlike Pyrus or Malus cultivar. So the first frost will kill the outer layer of tissue. So we want to generate as much phylloderm as we want, because the water application post-harvest is somewhat minimal, because ET is half of what it is compared to peak. So you're essentially replacing 30% of reference ET, which is 50% of 15% of crop evapotranspiration. So which would equate to about a half an inch a week.
Great. So I think with that, we've actually run out of time. I want to remind everybody that if you're interested in the program on December 15th on assessing fire damage in the vineyard with Kaan and Andy Walker, please register. You can use the link that Caroline had in the chat. She's also put a link in now for the slides that will be available for you from today's presentation. I'd like to thank Daniele and Kaan for great presentations and being able to answer all your questions. Really appreciate them taking the time. I'd also like to thank Karen and Caroline, Karen Block and Caroline Furman, for organizing today's program. We can't actually do these programs, even though it's office hours with Dave Anita. We rely completely on Karen and Caroline to put together these programs. So I really appreciate them doing that. And I'd like to thank all of you for taking time to attend. I hope you enjoyed today's presentation. I hope we'll see you on December 15th. So thank you to all of you for coming.
Thank you very
I'm gonna
much.
just say
you.
happy Thanksgiving, everyone.
Happy Thanksgiving.
Yeah.
Happy Thanksgiving, and thank you.
Happy Thanksgiving to everyone. Yeah.
Yeah. See you, Francisco.
Bye.